Thank you very much. So yesterday I said from 3D supersymmetric gauge theory, you should be able to get two vertex algebra. Should I denote it by VAT and VBT? So these are A twisted boundary VOA and B twisted VOA. And from 4D, you should get another vertex algebra. And this vertex algebra satisfy in particular associated variety of these ones. We cover Higgs branch. And so B twisted one recover a Coulomb branch. And so this one recovers the Higgs branch. And these are hyperkähler cones, and I think it's believed that the normalizations should be symplectic. All right. Symplectic singularity. So let me start today by recalling the definition of symplectic singularity. So our normal variety X, it is called symplectic singularity. If there exists holomorphic symplectic two-form on its regular part, such that the Hugubak of this form extend to the holomorphic form for any resolution of its extents to a holomorphic form. We don't require it's a non-generate, but at least extends to a holomorphic two form for any resolution. The singularity. But we can replace any by. And in this case, the X is automatically a Poisson because Poisson bracket on the regular locus extends to the thing by normality of X. And if X is a Poisson, affine variety, you can stratify the variety by analytic symplectic manifold. So you can talk about the symplectic leaves on this variety. And there's a theorem by Karadin. If X is a symplectic singularity, yes. The definition, are there similar for upstairs? Yes. No, it's just for, I think just for more. Yeah. Symplectic singularity, then this one has finitely many symplectic leaves. So in this case, leaves algebra by the result of Brown and Gordon. So simply the singularities have this nice. So this means these associated varieties should have finite remaining singularity. So yesterday I talked about the case of Katsumudi algebra. We consider the vacuum representation of G hat at level K. And I explained the associated variety is G invariant and the conic subvariety of G star. So if you want to find what vacuum representation that comes from closed, locally closed. So if you want to find something that comes from physics, you want to find a vacuum representation whose associated variety has finitely many simple leaves. And in this situation, so here leaves, simply leaves coadjoint orbit. So this means that this one has finitely many symplectic leaves. If and only if this variety is contained in the nilpotent cone of G. So by identification with the star by killing cone, this is an important. So this direction is easy if it's contained in the nilpotent cone because there are only finitely many nilpotent orbits. It's clearly finitely many. But the other direction is also difficult. So the question, so of course, if this one is integrable, then this satisfies, of course, this condition. But as I explained, this does not come from 4D because it's unitary. So the question we want to ask is when. this variety is contained in nilpotent cone. But because it comes from physics, it should be somewhat nice. So we want to find some nice representation whose associated variety is contained in the nilpotent form. And there's a natural choice for that. So integrable representation is, of course, nicest family of representation, which satisfies the semi-simplicity of the representation. So any integral module is completely reducible. And also the characters are modular invariant. But there are much larger class of representation of Katsumori, which satisfy these properties. So they are called the Katsuwaki-Moto admissible representations. So they all satisfy this the same properties. So it's natural to ask whether the associated variety of this representation satisfy this property. So definition. Should I define admissible representation? No. So there's no request. So I don't define. So it's defined combinatorially. So irreducible, you consider irreducible highest weight representation of jihad. So this is called admissible. If and only if following two conditions is satisfied. So first of all, lambda is regular dominant, which means that the pairing with any real roots is not non-positive integer. Or any positive real. So this means that the corresponding causalistic polynomial is trivial. So which means that the character is described by a wildcat type character formula. Something like that. So it's the same as the character of finite dimensional representation of G or integrable representation of G hat. The difference is only this part. So this is integrable wide group. So this is a subgroup of affine wide group generated by roots real roots, which is integral to lambda. So this is affine wide group. And so this one is just a set of real root whose pairing is integer. This lambda is integer. And the second condition is this integral wide. This group is not finite, basically. So the set of integral roots, Q span of Q integral roots is the same as the set of real roots. So this means that this wide group, which is a subgroup of wide group, which is a Coxeter group, is a infinite wide group. So which means this group contains translation point. And so if you write this character formula, if you separate translation part, this becomes some kind of theta function. So this means that the character has some modular invariance property. What is the difference between that and sorry. So this is a subset of real roots, but if you consider Q span, it's the same. So typically, so this has this kind of form, Q and delta. So real roots is of this form. This is the roots of G. And we just scale this diagram is. It's finite, isn't it? So this is a subgroup. In this case, corresponding wide group is integral wide group, the subgroup, but it's isomorphic to the original wide group. We just scaling this direction. And we are in particular interested in the vacuum module. Now this is admissible if and only if you write these two conditions. In this case, K is the shifted level is positive rational number. Here is a dual Coxeter number. Positive rational number, so written by some non-negative integer mutually prime. And this regular dominant condition means that this numerator is not too small. So P is equal or greater than some number. And this number is either dual Coxeter number or Coxeter number. And so this is if denominator. So our check is the Lacing number of G, which is a number of maximal number of maximal edges in the deakin diagrams. So 1 or 2 or 3, 1 for ADE, and 2 for BC, F, and 3 for Gs. And if you have check. And the theorem that suppose this is if denominator Q is 1, this means just LK is integrable. So admissible representation contains integral representation. But if denominator Q is not one, then this is not an integral representation. And this kind of situation happens when the first case, when denominator have this property, and Q is exactly this denominator. And when the opposite side, you find some root system of Lagrange. Anyway, the statement is that if this is admissible, the associated variety is a closure of some nilpotent orbit of G that only depends on the denominator. And so it's it, and in fact you can describe it directly. So the first case is just a set of elements such that adjoint to Q equals to 0. If check equals to 1. The second case is similar. So adjoint representation is a representation of G with highest weight theta, and you just replace this theta by highest short root. So this is highest short root. And so this to Q to Karchik equals to. So the fact that so it's important that there's a 2 here, because if there's no 2, this variety may not be irreducible. But because of this existence of 2, it's shown by Nakano et al. This variety is indeed reducible by case computation in most cases, and for other cases you can check.
So if you run our check then this
root system is a root system dual of GitHub. This is a vacuum representation of level K. So this is a simple quotient of the induced representation. Oh, yeah, yesterday. So I explained the R of LKG is a quotient of this kind of representation, and this can be identified with the quotient of polynomial function G star by some Poisson idea E, and so this was the zero roots. So. For example, the for type A, this orbit is so if you write in terms of Young diagram, this is the Young diagram as rectangular as possible. So it looks something like this. So you may not be able to divide Q n by Q, but just put rest of the boxes. So this certainly satisfies the condition that it has finite reminiscibility. And so you can ask whether they come from 4D, yes? Q is a denominator of K. So the least number that if you multiply K, it belongs to the integer.
Description is for admissible only, and that X is a locus of I. For admissible already.
Oh, in general. Yes. This follows from the definition. And so admissible vacuum representation do come from some 4D theory, which is some Douglas theory. Douglas theory. If it is boundary admissible. So meaning that the numerator P is as small as possible. So this was worked out by Song, Xie, and Yang. So so this variety only depends on the denominator. So you fix denominator, there's only one choice of P, so it comes from 4D. The conjecturally, other one do not come from 4D. And K is negative. K is mostly, it depends on P, but if P is small, it is negative. Yes. Oh, for boundary one, I think it's negative. Yeah. I'm not sure. And so obviously not all orbits appear from the admissible representation. And you can ask what kind of property these orbits have. And interestingly, exactly the same orbits appear as the wavefront set of metaplectic groups, which are Q-fold cover of the group corresponding G, which that appears in Manish-Stokes in periodic field.
Is this just an empirical fact or?
I'll say a little bit more. So we don't know why. Don't know why. And we can, so Manish talked about the connection of representation of a quantum group. And we find that if you consider the category of weight or over, but the weight representation of LKG. So this is a much larger category than category O, because we don't impose the highest weight condition. We just.
You mentioned that exists, but you gave explicit description of the source, right? Full lines, right? They're described.
Yeah, it's described, yeah.
And you're discussing now the same word.
Yeah, yes. It does.
You mentioned they're connected with my order, some metaplectic group.
For some reason. Yeah.
Because of some reason.
So this is related with representation small quantum group. So G or G check depends on the cases of the same root of unity as yesterday. So this was. So there are some interesting similarity. So we only proved for SL2. This category is blockwise equivalent to the category of unrolled version. So for this category. We are. And so I talked only about admissible cases, but there exists non-admissible working representation whose associated variety is a closure or nilpotent orbit. So, for example, if you consider so-called Deligne exceptional series, which is a series of A algebra and E algebra, discovered so this discovered by Gross Deligne. So this is a family of the algebra that has a property that everything, almost everything, is written in terms of dual external. And if you consider this kind of a sequence, and if you consider a special case when k equals to minus 6 over 6 minus 1, which is again expressed by dual external number, then it's possible to show that the associated variety is a minimal nilpotent orbit whose dimension is again expressed in terms of dual external. And so this for simply raised up. Okay. So what is new is that from the admissible case that for D4, E6, and E7, E8, this number is an integer. So for E6, it's a dual externalized 12, so it can be divided by 6. This is integer. And this case is not admissible. So these yellow ones are non-admissible example of this case. So D4, E6, E7. These are good, I mean, interesting. And if you look at this simply raised cases, so simply raised cases, so these are VOAs that comes from body theory. So they do come from body theory. And this is actually a first example they found in the original paper of Beem and O. And obtain from elliptic vibration via X7. So elliptic vibration is a vibration of curve by generic fiber elliptic curve. And so from this physicist apply so-called F theory. I don't know what it is, but it somehow gets some kind of coordinated theory. And this, you start with isotrivial elliptic vibration, meaning that the generic fiber is isomorphic. And the singular fiber are classified by Kodaira, and it's labeled by this simply based member of the Deligne series. And this one is exactly this vertex. And so until very recently, so description of the associated variety of the vacuum representation was very open. So there was not even a conjecture. But very recently, last week, Shan, Shan and Yang and Zhao gave a conjecture on associated variety of vacuum representation for simply based G. So they used the this observation. We have a picture, but there are many no admissible cases. So you want to describe this one for all K, which is a very difficult problem. And so we are covering duality map. So it.
But there are many more than 3, right? So,
there are many more. This is an example, yes. So yeah, duality map by Gao Yu E. Sure. G. So they consider a metaplectic dual. And then Lustig-Palestinian duality is extended to this metaplectic cases. And this kind of map is called a covering dual map. So somehow Lagrange duality appear in the description of the associated variety of the vacuum representation. So this is a very nice and interesting lecture, but it's very old.
Papers are very technical, right? With some special cases and more, right? So we use it, right?
So the usual duality map for type A is just you transpose the Young diagram, but you can. So it's a yeah you consider the point here is you consider some metaplectic group depending on this denominator.
Like this notation. So is it you take the metaplectic group of G and then affinize?
No. So yeah, we are not talking about orbits of affine. We are talking about orbit. So now let me explain more general situation where we find more interesting.
Well, it's the case when there are finitely many leaves, right?
Yes, it is.
So of course, because of singularities, right? And the second condition, which appears to be the key, you will explain why, right? That we need the not finitely many leaves, right? Okay.
So if it's simply singularity, it automatically has a finite.
Finitely some additional constraint, right? It does mean that there will be finitely many leaves.
So simply singularity implies finitely many leaves, but so because we are considering this a special case of G invariant closed subset of G. So in this case, the condition is the same as contained in a potential. But so we want to talk about more general situation. So I don't want to really define a vertex algebra. So if vertex algebra means that it's a vector space equipped with some map from here to here, which sends it to, sometimes we write YAG or sometimes write AG, which is a generating series of the operator corresponding A. So for each element produces infinite many multiplication indexed by n, and which satisfy the certain actions. And important satisfying certain conditions. I don't want to write them all, but the most important property is that it has the OPE. It has OPE. So it's written symbolically. This is symbolically like this, which means the which means that if you consider commutator of this generating series, so this makes sense as an element of n as a formal series. And this is written as sorry, this is this sum should be finite. Should be written as finite sum of so this is again element of V because AN is operator on V. So you can talk about the corresponding generating function. And so this is written divided differential of formal delta function, where delta function is and then one consequence of this OPE is either the if you consider commutator of each Fourier mode, this is expressed finite sum of M. So, by the way, can I advertise? And so there will be a book by myself and Amuro, whose title is I think, arc spaces. is vertex algebra and double algebra, I think, where we explain the detail of the definition of the vertex algebra. So anyway, so vertex algebra is something like this. And from vertex algebra, if you want to obtain Poisson algebra, what you do is the following. So you consider certain, again, quotient of V, and this quotient is span of this kind of element. And for Katsumudi case, so maybe I should explain example. So if V is this universal affine vertex algebra, and A is this kind of element, then corresponding field is just this uniquely determines the vertex algebra structure. So this is really a generating function of the elements of Katsumudi. And you can consider more general.
Equivalent to the previous definition, T minus two parameters.
Yes. And this is a Poisson algebra by so multiplication is given by -1 product, and Poisson bracket is given by 0. So the definition is two.
Here minus two, right?
It is
Then below minus multiplication.
multiplication.
Now here it is it's minus two. A little bit below, right? So the formula A bar times B bar to the right to say A
Minus, this is -1.
minus one.
This is 0. Actually, this is the same as span of A minus n, where n is equal greater than 2. So you forget this product and you pick up the first non-trivial, something you don't forget, and the next one. This is called the Zoo's introduced by Yeon-chan Zoo. And when did I? Oh. So yeah, so then you define the associated variety or associated scheme as a spectrum of this Poisson algebra scheme. Variety. So I don't have much time. So let me introduce the following. So we are looking for vertex algebra whose associated variety has finitely many leaves. So it's better to name such a vertex algebra. So we named it V squares this. If if XV has finite remaining any symplectic fields. So all vertex algebra coming from 4D or 3D should be quasi. So this captures, this gives a partial characterization of the vertex algebra coming from 4D. And then you can ask, what can you say about quasi-Ries vertex algebra in general? And the theorem is the following. So it will be quasi-Ries. Then, so in general, this vertex algebra may have or often have infinitely many simple representation. But if you only look at those representations whose character makes sense, so meaning that it's a positively graded and a graded component of its finite dimensional. Such a representation is called ordinary representation. And statement is it has finitely many simple ordinary representations. So if you assume V is simple, M0 is identified with V. And then, so this character makes sense. We can consider character of this representation. And this converges to a holomorphic function on upper half plane. So as usual, Q is considered to e to pi tau. And if you consider span of these characters, so this is contained in the solution space. Solution of so-called modular linear differential. Modular linear differential. So I don't have time to define what is a modular linear differential equation.
Converges, just some kind of a function, right?
Function is a function on the upper half plane.
What way converges?
So it's a formal series, but it can be considered as a function on the upper.
It is a holomorphic function, right?
Yeah, it is holomorphic function, yes.
Okay.
And so modular linear differential equation is a differential equation that modular form satisfies. And by definition, which I don't have time to discuss, there's a natural action of modular group. So this means that this generates finite dimensional representation of the SL2G.
Is it modular or just some kind of function?
It's a function which generates finite dimensional representation.
So no modularity, it's just some holomorphic function. Holomorphic, right?
It's a holomorphic function. If you add some, so I don't claim that this is equal because this modular linear differential equation sometimes have logarithmic solution. But if you add this solution, it's a modular standard.
But one simple ordinary, is it modular or one simple ordinary? Why it's not modular? Modular.
Yeah.
When it is modular, we're supposed to be like modular in many cases, right? No, okay.
So if a vertex algebra is very nice, if associated variety is a point and representation it's semi-simple, then it's shown by Yonchan-Zhu that the span of the character are indeed vector value modular form. And this extends his result, but so it's not as nice as the ideal situation, but still there are some modularities. And so theorem states some modularity property of the character of ordinary representation. And if you believe that its Schur index of 4D is a character of the Vacuum representation, it states this modularity of Schur index, which is, I think there's no other explanation in physics why this modularity should hold. And in particular, you can recover there are two central charges actually for 4D theory. And another one is called C central charge. Can recover A or C, I forgot. C central charge. Of 4D. By asymptotic behavior of the character. So it recovers some invariant for this. It's a good question, but it's a bit subtle. I don't have the right answer. And so I don't have time to explain. So I didn't. I said I don't claim this spans the is equal, but you can extend this result by considering Jacobi type character, adding one more variable. And then in some situation, if under some extra condition, you can show that this is exactly the space of a solution of a flavored modular linear differential equation, which is identified with the space of a one-point function of the twisted conformal blocks twisted by line bundles on an elliptic curve. So maybe I stop here today.